Everyone, I'm Sushanta Tripathy, so from INFN Bologna. I'm currently an INFN fellow here. So let me start the talk. I will talk about measurement of global observables with Alice at LHC. So as you all are quite experts, so I won't spend much time in the introduction. So just to show the brief evolution of the evolution of relativistic heavy ion collisions. So we have two large constructed nuclei are colliding in ultra-relativistic heavy ion collisions. And then we have a formation of deconfined state of quarks and gluons called as quark-gluon plasma. And then when the temperature cools down, we have the hydrogenation and then finally the freeze out. So after the freeze out, we detect the particles in the detector. So briefly, let us go through the Alice detector itself. So you can see, this is the picture of Alice detector, and you can see, assume the size of the detector based on the person standing here. Okay, so far Alice has been taking data since the beginning of the LHC run for run 1 and run 2, and currently run 3 is ongoing. And Alice has taken data for lead-lead, xenon-xenon, P-lead, and PP collisions. For PP collisions ranging from 0.9 TeV to 13 TeV, and then for lead-lead 2.76 and 5 TeV, and xenon-xenon 5.44, and P-lead 5.02 and 8.16 TeV. And for this run 3, which is currently ongoing, so we have the PP collisions at 13.6 TeV, and lead-lead collisions going up to 5.36 TeV. Okay, so in course of my talk, I will refer to large collision systems are basically the lead-lead and xenon-xenon collisions, and the small collision systems are referred to P-lead and PP collisions. So here is a event display coming from the central barrel of Alice detector. As you can see, these are the track and tracklets shown here. So, and then this is how the PP collisions event display looks like. Okay, so briefly summarizing, Alice has been taking data with in PP collisions in different collision energies, and we have a system size scan as well with PP going to P-lead, xenon-xenon, and lead-lead collisions in several different center mass energies. Okay, so key prospects of key thing about Alice central barrel is we have the 2-pi tracking, and this is very instrumental for particle identification. And the central barrel is basically it has lowest material budget in the central rapid region among all the experiments in the LHC. So here you can see that in the central rapidity range we have significantly lower material budget. And thanks to which we have excellent particle identification and continuous tracking over a wide momentum range. So in the left-hand side plot, you will see this the x-axis is basically the transverse momentum, and here the different particles are listed. So you have different particles which can be measured with the PID techniques, the pi Kp, deuteron, and several other anti-nuclei as well. And then we have gamma, eta, and pi informations through calorimetry or conversions. And then we have several particles which can be studied based on the decay channels. So here and these bars are basically the momentum range from which one can identify and study the particles. Okay, so then I will just briefly highlight the detectors which were used for the results which I will be showing in my next slides. The first one is a tracking system, which is used for the tracking and identification of primary vertex, and in some cases it is also used for particle identification. And then we have time projection chamber, which is a key detector for tracking and the particle identification. So I won't go through in detail about the particle identification because you already had a session on particle identification with the STAR and Alice detectors. So basically, with time projection chamber via the energy loss, one can identify the particles varying from pion, kaon, proton to antinuclei. And similarly, we have time of flight detector, which is where particle identification can be done by time of flight method. And then there are two forward detectors. One is V0 and another is 0-degree calorimeter. So V0 is used for the triggering purpose and as well as looking at multiplicity and centrality estimation. And 0-degree calorimeter is where 100 beyond 100 meter far from intersection point, and this is also used for measuring the spectral energy. And based on it, one can have the centrality estimation as well, and it is instrumental in measurement of beam lengths as well. And for the photon identification, photon detection, one is photon multiplicity detector, PMD. Okay, so let's start from a very simple picture, schematic picture of PP, p-ion, and collisions. So you see that we have, so basically the P is the impact parameter, and across different collision systems, so you have different event display. So for lead, P-lead, and PP. So the first thing one does when one study the global observables is looking at the centrality or multiplicity estimation. So by centrality multiplicity estimation, you mean that you specify the separate events based on the impact parameter in particular collision. Okay, so centrality is basically defined as basically the integration of impact parameter distribution in a particular impact parameter range and divided by the entire impact parameter distribution. And in ILS, how we obtain is we obtain with this formula. So basically, this NCS threshold is the particle multiplicity for the threshold. And in other way, one can also use the JDC energy threshold to obtain the impact parameter, obtain the centrality for linear collisions. So, and then one uses Monte Carlo based global model to fit the multiplicity distribution to connect to the geometrical quantities such as number of participants, number of binary collisions, and so here is a global Monte Carlo impact parameter distribution, and the right hand side is basically the multiplicity distribution, the end participant distribution. Okay, so so basically we use the so there are two methods by which we obtain the centrality. One is with the V0 amplitude. So we have a V0 detector in both sides of the ILS detector, A and C. So we use a V0, the distribution of, we obtain the distribution of sum of amplitudes in both the V0 scintillators, and we obtain this kind of distribution. And this distribution is fitted with a negative binomial distribution plus a global fit. So the negative binomial distribution is given by this, and the global fit is basically an ancestor. So we will be equal to the fraction of number of participants plus the fraction coming from number of binary collisions. So with this, one can estimate different centrality classes, and yeah. So the other method one can use is use the energy deposition in the JDC, 0-degree calorimeter. So naively, one would expect that the number of participants would be equal to 2 times the mass number, and minus the energy deposited by JDC over EA is the beam energy per meter. So as JDC, by the name itself, it's a 0-degree calorimeter. So it most of the energy what we see are deposited in JDC are basically coming from the spectra. However, in some cases, what happens is there are some nuclear fragments. Typically, they have Z over A similar to the beam, and these fragments remain in the beam file. Then this monotonic relation is not obeyed anymore. So one cannot directly use this kind of relation because of nuclear fragments staying in the beam file itself. Thus, with this using ZDC, one not very easy to one can model the centrality determination beyond 30 to 40% because this at the low centrality classes, we cannot have proper estimation of centrality with the ZDC. And when one correlates the V0 amplitude with the centrality estimation from ZTC, so we have a distribution something like this. So as you can see, we are unable to go to very far most peripheral collisions because as you know that LHC energy, so we are at very peripheral collisions, we have electromagnetic processes are dominated, so then it becomes very difficult to separate out this electromagnetic contamination from electromagnetic processes. So, okay, so saying that, so let us go to the multiplicity estimation in PP. So for PP, we do not have a direct analog of centrality. However, we use the multiplicity measurement, which serves to roughly separate the soft and hard processes. And using simulation from competing models, one can define better observables and apply the event selection criteria, event class separation criteria. So I would highlight a hypothetical picture of PP coming from one of the famous event generator at LHC, Spectral 8 event generator. So where one PP collision would have a primary hard scattering, which is governed by perturbative QCD, and then several soft QCD processes, which involves the low momentum transfer, and they are mostly governed by the non-perturbative QCD, and they include the underlying event. So the underlying event consists of the multi-path interactions, the initial and final state variation, and then the beam remnants. So combining this, so we have the underlying event, and then finally we have the hadronization, and we have the hadronization products at the end, and one studies the collective effects and several observables after the hadronization. Okay, so for multiplicity estimation in PP in Alice, we use different detectors in wide pseudo-rapidity range. So if one looks at the central pseudo-rapidity range, so one uses SPD, IPS, and PPC. And for forward rapidity, mostly we use V0M amplitude, which is basically the sum of V0A plus V0C. Okay, so let us come to some results now. So here is a plot of multiplicity at unit rapidity. So this PN chart delta is basically the charge particle multiplicity for unit solar rapidity range. And this is scaled with n part over 2. So that to study the bulk properties, how it scales with the collision energy. And you see that there is steeper rise with collision energy for AA collisions compared to the small systems. However, for P-led collisions, you see that when one fits this kind of dependence as a function of square root SNN with the power law. So you see that the P-led and D-gold collisions overlap with the inelastic PP collisions. Okay, so then going to the multiplicity distributions at mid rapidity. So in the left-hand side plot, we have the multiplicity distribution in different rapidity ranges from -0.5 to 0.5, -1 to 1, and -1.5 to 1.5 for PP collisions at 7 PB. And they have been fitted with the negative binomial distributions. You can see in these ratios, the fitting looks consistent apart from very low in charge. And the right-hand side distribution is the pseudo-rapidity density distribution. And here there is a comparison is shown for more central lead collisions, more central P-led collisions, and PP in L greater than 0 events. So in L greater than 0 events, it basically means that we are looking at those events where we have at least one charge particle multiplicity in the B0M rapidity, B0M rapidity range. Okay, so then let us come to the estimation of Bjorken transverse energy density. So thanks to this multiplicity distribution and the estimation of transverse energy density, we can obtain the transverse overlap area as a function of average n part. And here there are two kind of markers. One is basically when we have we've considered the nucleon with the exclusive area nucleon colliding with, and when you have only the participant which are considered only the nucleons, so you have two different markers. And using the standard Bjorken density formula, one can obtain this the lower limit of Bjorken density as a function of n part. So as you can see, there's a evolution going from p-lead collisions to lead-lead collisions. Okay, so then we have also measurement of inclusive photon production at forward rapidity. So this is one of the recent measurements for p-lead collisions. So the photon n gamma, the photon multiplicity measurement has been done for thanks to the photon multiplicity detector. So these are the blue markers, and then we have published NSA's fluid rapidity density as well. So you can see both the inclusive photon and charge particle products in the meter 50 are actually described fairly well with models. Okay. So then I will move to one of the key measurements we do for global observables, the underlying event measurements. So basically, I've already highlighted this. So the underlying event are the collection of particles which do not originate from the primary hard partner scattering or the related fragmentation. So these includes the multi-partner interactions and beam remnants and initial and final state radiations. The conventional for the conventional UV analysis, what we look for is we actually study the particle production in three different topological regions, with respect to the leading particle. So we have a toward region, transverse region, and away region. And the main underlying event observables, what we study is the charge particle density and the sum transverse momentum density. So here is a plot of charge particle density as a function of PT leading, the leading PT of the event. So, and this is for PT collisions at 13 dB. So these different markers are basically for different regions toward away and transverse region. So as you can see, there is a steep rise and the event activity for all topological regions as a function of PT leading. But after PT leading greater than 5, so the charge particle density in the transverse region remains almost insensitive to hard component. And the increase in PT leading in both the toward and away regions, the charge particle density scales with the hardness. Okay, so this will be one of the key features which I will come to it again in my later part of the slides. So thanks to this feature, we can use one of the event-safe observable called relative transverse activity classifier. Okay, so and then there's a measurement of charge particle density for both PP and P-lead collisions, and these are the results for transverse side basically. And as you can see that there is a larger UV magnitude, the underlying magnitude, and P-lead collision. Okay, so and then one can correlate the underlying event measurement in the mid-rapidity with forward energy measured in the Alice 0-degree calorimeter. So one could naively expect that the forward energy measurement would give a complementary measurement to the conventional UV analysis. And to see this is both these observable, let's say the underlying event activity measured by the charge particle density and then the Zn energy. They both are quite complement to each other, and basically forward energy is completely anticorrelated with the mid-rapidity activity. So it's basically if you measure small for energy, then so we are selecting very high multiplicity events and high PP leading particle in the mid rapidity. Okay, so with this info, so let us look at the evolution of hadron chemistry with multiplicity and centrality classes. So to study the particles, both charged particle and or identified particles, one uses several correction method. So you have to correct the final measurement with the detector efficiency cross acceptance, as well as you have to correct it for fit down correction. So in most of the results analysis, so we use global tracks where the information from ITS and PPC are included, as well as for particle identification, we use other detectors like time-of-flight detector. So what this global tracks are basically set up. There are for these tracks, we have set up trackers, which keeps a good resolution in transverse distance of closest approach, DCXY distribution to the vertex. And in this way, we have a good separation of primary and secondary particle. And this is one of the key thing to we actually work a lot on this to have a careful subtraction based on the DCA so that we are only choosing the primary particle. So primary particles are those particles with the mean proper lifetime tau larger than 1 centimeter per C, which is either produced directly from the interaction or from the decays of particles with the tau smaller than 1 centimeter per C, but excluding the particles produced in the interaction with the detector material. So in the left-hand side, we show the global track acceptance for the efficiency as a function of PT for different centrality classes for pi, k, and p. And the right-hand side plot is the DCXY distribution. So here you can see that this data is this marker open circle, and you will see the contribution coming from weak decays, material, and primaries. So based on this combined fit, we separate the fraction of the primary particles. And after applying all the correction method and then the estimation of the systematic uncertainty based on these variation of track cuts as well as the event quality cuts. So we obtain different particles, the integrated yield of different particles. So starting from pion, kaon, and reaching up to antinuclei. So here we have the integrated yield for all these particles, and this has been compared with the thermal model, the statistical hadronization models, and as you can see that with the very wide magnitude of the particles, so like almost like 9 order of magnitude, the common model is the statistical hadronization models are very successful in explaining the integrated yield of each particle species. In the below, you have the deviation with respect to so how much the thermal model deviates with the data, and you can see that they are more or less consistent to 0. And this implies that hadron subject to chemical equilibrium close to the QGP transition temperature, and the chemical is about 156 MeV. So then to go into more differential part, so one can obtain the particle spectra, particle transverse momentum spectra. So here you have the transverse momentum spectra for different particles, pi, k, p, and going up to omega for different multiplicity classes. So these results are for PP collisions in different V0M multiplicity classes. To remind you, V0M, I refer to the sum of V0 amplitude coming from A and C detector. So, so here are the different multiplicity classes listed here. And when one takes the ratio to the initial greater than 0 events, so initial greater than 0 events are pretty much similar to the minimum bias events, except the fact that we are only looking at the events which have only at least one charge particle. So when one takes the ratio, you can see that the ratio is taken where 2 is greater than 0 for two different multiplicity classes. Multiplicity class 1 is high multiplicity. This 9 is basically the low multiplicity class. So this plot is a function of PT. So you see that here at low PT region, there is a mass ordering, and at high PT region, the behavior is something like the proton, the Mason variance separation seems to be seen, but based on high statistical as well as systematic uncertainty, this cannot be. Well, it is not very significant, but we see a similar behavior of radial flow from where we expect radial flow. The mass-like behavior, and surprisingly enough, even for low multiplicity class, we see this kind of mass dependence behavior. Okay, so and then we also have transverse spectra for different particles here for leaded collisions as well. So here I'm only highlighting the pion, and proton. So from all these transverse spectra measurements, one can actually look at a closer look at the spectral shapes as a function of multiplicity using a simplistic hydro model, blast wave model. So if one does a blast wave fit, a simultaneous fit of blast wave with using the particles which are mostly abundant, pion, and proton. So in left hand side plot is for PP. So here this blast wave fit has been done for pi kp. And then based on that, we have blast wave prediction for other particles. And then in the right hand side, you have the kinetic bridge of temperature and the transverse flow. So this is the correlation plot. And as you can see that at a similar multiplicity, so the smaller collision spectra is a bit harder. And with the these are basically the lead collisions. So you can see that you have a higher transverse flow and lower kinetic bridge of temperature. And please keep in mind that these blast wave fits are very sensitive to the fitting range when one does the fitting. Okay, so and then I will move to the one of the another interesting measurements, strangeness production. So based on the V0 selection criteria, so we obtain the invariant mass spectra for K short, lambda, xi, and omega. Different they have like different strangeness content. So and then this has been this invariant mass spectra has been fitted, and then we obtain the PT spectra for each PT pin. So basically for each PT pin we have this invariant mass spectra, and then we fit it, and then we obtain the PT spectra at the end. And from the PT spectra, one can calculate integrated yield. So then these integrated yield are actually used for the particle ratio study as well. So here is a summary of different the particle ratios of the different strange particles. Let's say proton is non-strange, of course, and pi is hidden strange. So these are in the same plot itself. We have K short, lambda, xi, and omega. And here in this plot, we have this ratio as a function of charge particle multiplicity. When you look at this lower region, it's basically low multiplicity PP collisions. And when you go towards a high charge particle multiplicity, they are more central level collisions. So you see that there is smooth evolution of hadron pion ratio across the multiplicity. And as you can see here, we have different collision systems as well as for different collision matching. And they seem to be, these ratios are seem to be independent of collision energy and the system. Okay, and as you can see, this the enhancement of this strangeness production increases with the strangeness content of the particle. So this is with the increasing strangeness content. and phi meson is a hidden strange particle. And if you I might have seen in 2017 we have publication in Nature Physics where the strangeness announcement has been reported in high multiplicity collisions, which is very similar to what we see in the central collisions as well. Okay, so with this, then I will move to the production of resonances. So in Alice, we measured several resonances. So the key ones so here are K star 0 and phi. So for these cases, we actually do inverted mass spectra analysis as well. And here we have inverted mass spectra for K star 0 and phi. And this has been fitted with Breit-Wigner distribution function and Bjorken distribution function. So Bjorken distribution function is basically the convolution of Breit-Wigner with Gaussian, and as phi has very small width, so one has to take into account the mass resolution. That's why we have this convolution with Gaussian distribution. So this study has been repeated for all the P2 bins, and then we obtain the PT spectra, and then we obtain the particle weight ratio. So after integrating the PT spectra. Okay, so here is a summary of all the resonance production. So here it is again shown as a function of d inside d to the power 1/3. And here, starting from rho 0 to K star plus minus, then lambda, then phi. So increasing in the increasing order of the lifetime of the particles. So what we see is there's a significant suppression of short-lived resonances, which are basically attributed to the hadronic stacking. So when I say significant suppression, which is it is with respect to the small collision systems or with respect to low multiplicity collisions, and using this fact with respect to the PP collisions, one can obtain a lower limit of hadronic phase lifetime as well. However, for long-lived resonances, they are hardly one sees as suppression. So I think there is weak suppression or almost no suppression at all for xi and phi particles. And yeah, so you are using with this kind of suppression, one can obtain a lower limit of hadronic phase lifetime, and from rho 0, K star, and lambda, this has been calculated, and this is shown as a function of the inside theta. Yeah. Okay, so there's a evolution of this lower limit of hadronic phase lifetime as a function of the inside theta as well, indicating the higher suppression for more central layer collisions. Okay, so and then I will move to the multi-difference studies with events of observables. So thanks to the enormous data collected during run 2, and which is going to be collected in run 3 over vast amount of data. So this is this kind of studies, multi-difference studies are very important in the coming days. So we have several measurements so far with the run 2 data with multi-difference studies with events of observables. So when I'm talking about events of observables, we are already having a cut on the charge particle multiplicity. Then we are looking at different event sets. So that's why it is called multi-difference. Okay, so one such observable is called transverse spherocity. So spherocity is given by this formula, and here you have to find a unit vector which basically minimizes this ratio. And this pi square by 4 is the normalizing value, so that your sphericity ranges from 0 to 1. So when the transverse sphericity is tending to 0, you have a back-to-back structure. And when the sphericity is tending to 1, this you are looking at the isotropic events. Okay, so then we have identified particle production as a function of transverse sphericity. As I said earlier, we already have the charge particle selection. Then we are looking at the transverse sphericity. So for the charge particle multiplicity estimation, we use first the P0M estimator. So here, these are the plots of the PT spectra for pion, kaon, proton, and psi. And you see that in the ratio, so these red markers are for Jet events. When Jet I'm saying spherocity tending to 0, and then the isotopic events are the blue marker. So in the lower plot, we have the ratio to the spherocity integrated phase. So for the Jet and isotopic. So as you can clearly see, these event shape observables are very instrumental in separating out the events where which is dominated by the Jet or isotopic events. And this is also can be seen for other particles, kaon, proton, and psi as well. So, and again, we also study the same thing in the mid-rapidity estimator as well, which is done with the SPD detector. So here, when you compare the V0M rapidity and an SPD mid-rapid estimator, then you see that for pions, kaons, and protons, the particle collection from PT events dominates from a lower PT pay when compared to the V0M estimator. So one summarizing, like if you look at mean PT, mean PT basically gives the info about the slope of the PT spectra. So mean PT is a function of, when you look at mean PT as a function of the integrated yield of pions, we see that the mid-rapid estimator does a better job of disentangling the soft and hard events more accurately with a very small multiplicity. So with this SPD triggered events, we obtain different particle ratios to see to probe the radial flow effects. So you see this this is for P over pi ratio as a function of PT for isotopic and Jet events as well as for integrated events. So as you can see that the P over pi ratio is enhanced in the intermediate PT in the isotopic events compared to the Jet ones, and which is very similar to, and it's reminiscent of a similar effect observed in magnetic collisions. And in the measured PT interval of so for Xi, we cannot go very far in PT. So for Xi in the measured interval, we see that the strange particle production is higher in isotopic events than in the Jet events. Okay, so then I will come to another event set classifier, which is called relative transverse activity classifier. This uses the info with these event set observable. You can study the finite state particle with different underlying event activity. So if you have an so basically this RT distribution looks something like this. And using RT, one can actually vary the magnitude of the underlying event and then study the particle production. So if you are looking at RT tending to 0, then you are looking at low underlying event activity region, low underlying event activity events. And then with the high RT, you are your underlying event starts to dominate. So for the RT distribution, we have to apply a PT cut on the leading particle because we have to ensure that in the transverse region, we are not biasing this because the RT is calculated in the transverse region. It's basically the charge particle multiplicity in the transverse region divided by average charge particle in the transverse region. So we have to ensure that we are not biasing the RT distribution with the selection of the leading particle. So this PT leading greater than 5 cut is applied, where you see that the charge particle density is insensitive with the PT leading. Okay, so using this RT, different RT cuts, so we can obtain the mean PT as a function of RT for different topological regions like near, away, and transverse side for different collision systems as well. So PP, P-like, and L-like collisions. So if I take your attention to low RT region, so you see that at low RT, all the collision systems like PP, P-like, and L-like collisions have the same value of mean PT across topological regions like near, away, and transverse side. So basically, when you are looking at RT tending to 0, then you have only events which are Jet dominated. irrespective of the collision energy. So this is what we see here, and this is what one would naively expect. And then when one increases the RT, so we have a higher underlying event contribution, and this in this way, all the three topological regions are approaching to the value what we see in the transverse side, because they are mostly dominant in the underlying event contribution. And we have also measurement of identified particle production as a function of RT. So here also you see that, so basically RT is also quite complementary to the spherocity estimation, because in that case as well, so you are actually looking at the jetty events and isotopic events. So here you are looking at the events which very less underlying event and very high underlying event. So here there is a PI ratio in the transverse region as a function of PT. So you can see that there is this 2.5 to 5 is basically the high underlying event contribution region, and then 0 to 0.5 is a low UV region. So here we see a radial flow-like features, and when we look at xi over pi ratio, so basically we obtain this result for all three topological regions. So here we are highlighting the transverse and toward region. So when you look at the xi over pi ratio, this shows a similar trend as we see for P over pi ratio as well. So these events, this relative transverse activity classifier actually helps to understand the interplay between the underlying event and the jet-like components. Okay, so with these results, then I will give a brief outlook about the run-3, which all of us are expecting to come out very soon, because the run-3 is undergoing, and so far we had PP collisions at 13.6 TeV, as well as some pilot beam of PP 900 GeV. And recently we had a leaded collisions pilot beam at 5.36 TeV. So the key upgrades are done for the LHC Run-3 are there's an improvement of ITS, which is called ITS2. So the innermost layer is now closer to the interaction point, and we have there is a significant reduction of the material thickness, and we have a new detector of muon power tracker, which improves the muon tracking, and then we have new TPC GM-based readout chamber, and there is a new fast interaction trigger detector, and there is new readout for all detectors, and new online on offline system. So from that, here are the couple of performance plots coming from the TPC and the top TPC energy loss and time of flight as a function of momentum. So here, these are the results coming from pilot beam, which has taken place in October 2021, and this looks pretty much so. This provides a benchmark, and we are ensured that everything is fine, and then to progress with the PP 13.6 TeV results. So here are the charge particle multiplicity, or basically the pseudo rapid density comparison with the pilot beam data with the published results what we had in the run-1. So here you see that results obtained from ITS2 are quite consistent with the previous analysis publication. And this provides a benchmark for tracking and reconstruction, and as well as for new analysis. Okay, so with this, I will summarize my talk. You can see that I listed several comprehensive set of measurements of flow observables. It's available in our list. Of course, I could not cover everything, but hopefully I have shown some glimpse, and I mentioned few technical details about how to obtain this kind of observables analysis. And as you can see, the enormous amount of data for different collision systems are already taken, and we will have several more results from run-3. And we observed strangeness enhancement and collective effects, which are seen in high multiplicity and P-led collisions, which are reminiscent of effects observed in heavy ion collisions. However, it is still not, we still not have seen the jet modification effects or jet pinching effects in small collision system. So it is still far from hard to understand that whether we see actually um, quark-gluon plasma droplet kind of effects in small collision systems. So, and then as I have already shown, resonances are quite instrumental in probing the hadron phase lifetime. And the multi-differential studies based on the events of observables like transverse spherocity and relative transversity classifier, they help to distinguish soft and hard events. And they are going to play a key role in the run 3, analyzing the data of run 3. And so I would say stay tuned for more and more new and high precision results because as you have seen, there are several results which have very high statistical uncertainty and systematic uncertainty. So we will have more high precision results from run 3 of Alice, run 3 of LHC, and hopefully so early next year we will release many results soon. So many thanks for this invitation and many thanks for your attention for this talk. Thank you very much. If you have some questions, feel free to ask.
Thank you, Sushant, for this nice talk. So this is now open for questions, answers. I see Subhash has already raised his hand. Subhash, you want to go ahead?
Yeah. So thank you, Sushant, for this very nice comprehensive talk. I have a question on your slide 41. So how do you do this feed down correction in Alice? Like, is it driven by the data, or you did kind of driven by the models? Like, there are two ways you can do feed down. Could you elaborate a little bit on it?
Yeah, so basically we get an estimation from models for weak decay material info, and then we so weight it with the data-driven particle composition. So as you know that in models they don't have proper fraction already with their models, so they because they do not have an exact weak decay in their model. So like mostly some of the results are the models we use are PICIA and HiSync for PP and heavy ions. So we later then data-driven particle composition has been also corrected for, and we do a template fit to obtain this fractions of primary. Is it clear?
Yeah. I get your point. So are there any difference in the feed down fraction if you use, for example, the data-driven template and you use only the Monte Carlo? Are these two fractions same, or are there any difference between?
So they have some percentage of difference. So let's say if you are looking at charge particle multiplicity, then probably the difference is very less. But if you study the nuclei production, so there your this kind of the fraction coming out for nuclei would be very significant. So that is why we across all the particles we do this data-driven fit to have the proper fraction of the primaries. And there is based on the fitting ranges of this template fit, we also have some systematic uncertainties which are going to the final plots as well.
Okay. Subhash, is that okay?
Yeah. I got it. Yeah. Thank you, Sushant. Yeah.
So we have a question from Rishi. So you have to go to slide 57. So the definition of sphericity is with collinear shape.
Yeah, it's infrared and collinear shape. Yeah.
Rishi, you want to ask further?
No, okay, yeah, that's
okay. Any more questions?
Hello.
Yeah.
Hello. Hello, Susan bhai. Nice talk. I have a doubt on slide 55.
55. 65 or 55? 55, right?
55. 55.
Okay.
Uh,
Yeah.
Usually we use this resonance yields to calculate this lifetime of hadronic phase. But I have also seen that this lifetime what we extract from this toy model,
Yeah.
this is almost equivalent to the lifetime of the resonance itself. Like if we do the k star, use this k star to extract this comes nearly around 4 to 5 for me, or 6. Sometimes in Alice, I have also seen that it goes to 6, 7, something like that. And similarly, lambda for lambda and all, it is around their lifetime itself. And you can see, also see that using different resonance, we are getting different lifetimes. So how can we interpret this thing? Because at the end of the day, we are measuring the lifetime of the fireball, and it is
Yeah. Yeah.
clearly
So
particle dependent. Yes.
So with this toy model, one cannot have the exact value of the hadronic phase lifetime. So what we can only have is the lower limit of the hadronic phase lifetime coming from different resonances. So you said that the values are very close to the lifetime of the resonance, but it is not the case, right? Because there is a smooth evolution as well. So if you go to the most central cases, so you have higher value of the lifetime, or what we get. So lower limit of lifetime, and then when you go to the low multiplicity region, so you have lesser values, right? And the key thing to note here that with the increasing in charge particle multiplicity, we have significant suppression, and then the lower limit of hadronic phase lifetime increases. So this was the point to highlight here. And in the models, for example, post 3, where your PMD is used for the hadronic scattering. So this gives also the values very close to what we get from the resonances. Yeah.
Thank you.
So there seems like some kind of mass ordering in this.
Yeah. So this we do not completely understand, but yeah. So let's, for example, for lambda at low multiplicity, we have very high statistical uncertainty, systematic uncertainty. But yeah. So after
But
all,
at
this
high
is a,
multiplicity, indeed the error bars are under control, right?
yeah, yeah.
And
So
there
this,
seems to be this kind of an ordering that the lambda star has the largest, largest lifetime compared.
yeah.
The lifetime that we extract from the lambda star yield is the largest, right? Followed
Yeah,
by
and yeah, there is a the previous point asked by Sweeney is that lambda has also higher lifetime and rho has a lower lifetime. So, but this, yeah, this I'm not sure the theoretical interpretation, but this is a good point to look into.
right.
But one should remember that with this toy model, one cannot have the exact estimation of hadronic phase lifetime. It's basically a lower value. And this plot, we are just highlighting the evolution of this hadronic phase lifetime with the matrix.
Okay. Any more questions?
This is Duhisha. I have a question on slide 68.
68. Okay.
68.
Yeah.
Yeah, this slide in the last plot, like transverse side, if you look the higher RT value, like the PP results, even though uncertainty, but PP points are costing the period points.
Yeah. Okay.
Is
So
why we expect, is there any reason like underlying event you expect more in period case than PP, and you look this observable to suppress like underlying event, right? If I
so basically what one would expect is when you are going to the high RT, so everything should be dominated by underlying event. So because these are the high RT region. So yeah, so you have a good point that when you look at
That I understood. For you going
Yeah.
for RT to understand the underlying event, but the different sides like near side, our side, and transverse side. The main idea of the transverse side is what? Like you understand the particle production which is either coming to JT or not, right? If I understood.
So the transfer side is basically you are looking at the transfer center. So basically, when you're looking at transfer side, we are only probing about what happens in the underlying event region, right? So because that's where you define the underlying event region, and then away and transfer side, away and near side are the jet applications of physical region. So yeah, this point you are saying, this is an interesting point, but within uncertainty, actually, I'm not
But it
sure.
is crossing like
Yeah.
between 2 to 3, it starts crossing. Okay, it's within uncertainty, you can make any comment, but even though hierarchy, can I understand like if you go hierarchy, it suggests there is a more contribution of underlying event, but still in
Yeah.
case of between PP and PLET, let's PP start to dominate in the hierarchy. That can I get this information from this plot? That's why I think. But okay, this uncertainty is within uncertainty, you cannot make statement on this, but it seems to something is happening. Some okay.
Yeah.
Thank you.
Okay. So probably this is a point to look into the upcoming data. Yeah. So
Yeah. Thank you.
thanks for this.
Thanks, Vikisham. Any further questions? Okay. Looks like no more questions. So Rishi, shall we first stop the recording?